All right, in this video, we're going to look at function transformations, another type of rigid transformation, and that is reflections. Remember, a rigid transformation is one that does not affect the shape of the graph. So he says, it says here, let f of x be the function below. Graph g of x equals negative f of x. So why don't we just try what it says? We have our x values here on the left. We're going to just input them into g and see what we get. So I see that g of 0 would be negative f of 0, which should be negative 1, because f of 0 is 1. So that means the point on g of x would be 0, comma, negative 1. Plugging in 2, we see g of 2 equals negative f of 2, but f of 2 is 3, so this is negative 3. So the point is 2, negative 3. Plugging in 4, g of 4 is negative f of 4, but f of 4 is 3, so that's also negative 3. So we have the point 4, negative 3. And then finally plugging in 5, we get g of 5 is equal to negative f of 5, but f of 5 is 5. So we get negative 5. So we've got the point 5, negative 5. And so if you look at what happened, basically our y coordinates are here. Our y coordinates on the graph of f are now their opposites. Okay, and so what that causes is a reflection over the x-axis, as we see happening in this picture here. Right? All the y coordinates are the opposite of what they were for each given x coordinate. So just to generalize, using our fundamental graphing principle, which states that if AB is on the graph of y equals f of x, then f of a equals b. So if g of x equals negative f of x, then when x is a, we say that g of a would be negative f of a, which is negative b, since f of a is b. So that means we would plot the point a, negative b, if we were interested in the graph of g. And so what this causes is a reflection over the x-axis, right? So I'm just going to say y values are the opposite of what they used to be. Okay, and so that causes a reflection over the x-axis. Okay, so that's a type of reflection. The other type of reflection would be a reflection over the y-axis. So let's examine what happens here. Same function to start with, f of x is pictured below. We have its points. G of x is f of negative x. So again, as usual, it's sensible to just try plugging these values in. So I'm going to start plugging in these inputs over here on the left into g. So g of 0 equals f of negative 0, which is f of 0, and that's 1. So we get an output of 1. So the point 0, 1 is on the graph. G of 2 would be f of negative 2, according to this rule. Now we have a problem, because negative 2 is not in the domain of f, because this is the domain of f, those 4 points, or those 4 points and values in between. Maybe it's best to look at the graph. Negative 2 is not in the domain. The domain goes from 0 to 5. So we don't know how to do this. And similarly, we're going to run into a same problem down here. So this strategy is not going to work. We can't just directly input the old x values. So as in a previous video, when you're dealing with transformations involving your x coordinates, it's best to think differently. And the way we're going to think here is we're not thinking about these inputs as being our new inputs. We're thinking those as like our old inputs. The question is, what are the new inputs? So what we need to do is I'm going to copy those down here in this left column. So I'm going to move those here, 0, 2, 4, and 5. And the reason I'm doing that is because once, if you look at how G is defined, once what's inside the parentheses for f is a familiar number, like 0, 2, 4, or 5, we know exactly where f will send that input. So what we want to know is what does, and so I'm going to think of these as like my new, these are my new inputs there. This column is my old set of inputs. We want to know what we would have to plug in, what our new inputs would have to be to yield the same outputs that we've gotten before. So just for example, let's start with f of 2. So we know that f of 2 is equal to 3. The question is, if I wanted f of negative x to become a 3, what would x have to be, x being our new input? Well, if we just set those equal, negative x equaling 2 tells us that x equals negative 2. So we know that negative 2, oops, wrong place. We know that negative 2, right, would be our new input that would yield the same output. What about, let's for instance, f of 4 is equal to 3. If we wanted f of negative x to be 3, the question is, what would our new input have to be? What would x have to be? Well, let's just set it equal to 4. Negative x equals 4 implies that x is negative 4. So we would need that to be negative 4. So I think at this point you can understand what's happening. Our x values are the opposite of what they used to be. So the inputs for G, in order to yield the same outputs that f does, they need to have the opposite sign. They need to be opposites. And of course, you can check this. I'll do a few in here. If we were to plug in, well, this one worked above, so this won't be too shocking. G of 0 would be f of negative 0, which of course is f of 0, but we know f of 0 is 1. So we plot the point 0, comma 1. That's on the graph. G of negative 2 would be f of negative negative 2, which is f of 2, which we know is equal to 3 from the table above. So we plot the point negative 2, 3. Okay, so in similar fashion, I'm just going to put dot, dot, dot here. We know that the point negative 4, comma 3 is on the graph, and we know the point negative 5, comma 5 is on the graph. That might have seemed like overkill because, you know, you might have come to this video with more prior experience with transformations. But what I'm doing here, especially in between the two tables, can be very helpful, especially when you get kind of crazy transformations. So I'm kind of trying to follow a pattern here that'll help you understand things in the future. But in any case, what you should notice is that your x values here are the exact opposite of what they used to be. That causes a reflection over the y-axis. And so if we go look at the graph, we see when we plot those points, our old function gets reflected across the y-axis. And to generalize, we see that if using the fundamental graphing principle, if AB is on the graph of y equals f of x, then f of a equals b. So if g of x equals f of negative x, what we want to know is, so we know that f of a equals b. The question is, if we want f of negative x to equal b, how does x and a relate? So negative x would have to equal a, implying that x equals negative a, x being our input for g. And so what that tells us is that g of negative a, again, according to the rule, is equal to f of negative negative a, which is equal to f of a, which is equal to b. So that reasoning on that one point kind of tells the whole story. It tells us that on the graph of G is the point negative a, b. This telling us that we would be that our x values are the opposite of what they used to be. Okay, and that causes a reflection over the y-axis. And to just finish off with a summary, here is a summary of what happened and how you'll think about these when you have to do transformations on your own. So if f is a function to graph y equals negative f of x, you're going to reflect the graph of f of x across the x-axis by multiplying the y-coordinates of the points by -1. And you're going to graph f of negative x by reflecting the graph of y equals f of x across the y-axis by multiplying your x-coordinates by -1. So I hope this helped you understand reflections, and in a future video we'll talk about scalings, compressions, and stretches.